Welcome to this video on kinematics, where we're going to explore a car stopping due to a tree fallen on the road. You are driving with a velocity of 90 kilometers per hour, 25 meters per second, and notice a tree has fallen on the road 55 meters in front of you. If you immediately slam on the brakes and come to a stop in 4.5 seconds, A, do you hit the tree? And B, what would the car's acceleration need to be to stop right at the tree? Before we find if we hit the tree or not, let's set up our physics question. We put our variables down the left-hand side, and we draw a small diagram on the right. Let's start with our diagram, because this question has a few subtle details which can cause people to stumble. Our car here has a velocity initial equal to 25 meters per second, and a velocity final at the tree, before or after, regardless of whether it hits it or not, equal to 0 meters per second. In this question, the tree is 55 meters away. D is equal to 55 meters away from the car. And the car stops for a time of 4.50 seconds. So our T is equal to 4.50. Now we can carefully write our variables down the left-hand side. So you are driving with a velocity of 25 meters per second. That's our VI. Just like in our diagram, VI is equal to 25 meters per second. We come to a stop, so our VF is equal to 0 meters per second. And we stop in a time of 4.50 seconds. So T is equal to 4.50 seconds. We're trying to figure out if we hit the tree or not. So we need to calculate how far we travel, our D. You need to be careful because the 55 meters given in the question is not the distance you stop in. The 55 meters given in the question is the distance the tree is from the car. So the distance we stop in could be less than 55, more than 55, or in this one case, it could be exactly 55. For completeness, we can mention the acceleration here. However, we're neither given the acceleration in the question nor asked to solve for it, so it doesn't matter if we add it or not. We're now ready to pick the kinematic equation we want to use to solve this problem. We need an equation that has VI, VF, T, and D. So any of the equations that have A in it are not going to work for us. So if we look through our equations here, this one has A, this one has A, and this one has A. So these aren't going to work for us. The only equation that's going to work for us is this one right here. So the distance it takes to stop is equal to our velocity final plus our velocity initial divided by 2 multiplied by the time it takes us to stop. Let's add in some numbers. The distance it takes to stop is what we're looking for. So our D is equal to our velocity final, which is 0 meters per second, plus our velocity initial, which is 25 meters per second, divided by 2. This is all multiplied by the time it takes to stop, 4.50 seconds. We can clean this up a little by rewriting it without the 0. So D is equal to 25.0 meters per second divided by 2, all multiplied by the time, 4.50 seconds. 25 divided by 2 is 12.5. So 12.5 meters per second. D is equal to 12.5 meters per second multiplied by 4.50 seconds. 12.5 meters per second multiplied by 4.5 seconds gives us a final answer of 56.3 meters, because our seconds on the top cancel with our seconds on the bottom. Do we hit the tree? Well, yes, the tree was 55 meters away and we traveled a distance of 56.3 meters. Let's just add this to our variables on the side. 56.3 meters. And now let's look at part B. In part B of this question, we're asked to find what the car's acceleration would need to be to stop right at the tree. Now we need to be careful. There's some subtleties in this question. So let's look back at our variables in our diagram and make sure we understand what we're actually looking for to ensure we get the question correct. In part B, we are told the car stops right at the tree. So our displacement is 55 meters. Our displacement from part A is no longer valid. So D is equal to 55.0 meters. Similarly, our stop time from part A is no longer valid because we know that stopping in 4.50 seconds takes us 56.3 meters. So in part B, we actually don't have a time to use. So let's also remove our time from our diagram before we find a kinematic equation that has a VI, a VF, a D, and the A that we're looking for. We need a kinematic equation that does not have the variable for time. So this one won't work, this one won't work, and this one won't work. That leaves us with this kinematic equation. So let's write it at the top before we start solving. VF squared is equal to VI squared plus 2AD. It's time for some numbers. Our VF is equal to 0 meters per second. Our VI is equal to 25 meters per second. We have the 2. Our acceleration is what we're looking for. And our D is equal to 55.0 meters. All that's left is the math. Here, 0 squared is 0. This is equal to 25 squared, which gives us 625 meters squared per second squared, plus 2 multiplied by 55 gives us 110 meters, and our variable A. We need to get A all alone, so we start by subtracting 625 from both sides. This gives us negative 625 meters squared per second squared on the left-hand side, and our 110 meters multiplied by our acceleration on the right. And finally, to get our acceleration all alone, we divide both sides by 110 meters. So on the left, we end up getting negative 5.68 meters per second squared, which is equal to our acceleration after our 110 cancels with our 110. And if you're wondering about our units, well, we had meters squared per second squared divided by meters. So meters squared is essentially meters times meters. So we canceled one of the meters on top, so we'll just get rid of the squared with the meters on the bottom, leaving us just with meters per second squared. The negative acceleration is exactly what we were expecting. We defined the positive direction as towards the tree. So if we would have ended up with a positive acceleration, we would have actually been speeding up towards the tree. But we were slowing down or accelerating in the negative direction, which is opposite the direction of our initial velocity. Thank you for watching this video on kinematics, where we looked at a scenario of a car slowing down. And we learned some important lessons about paying attention to the small details in a physics question.